In the context of quasi-linear preferences that we discussed in the last module, we saw that the outcome of the social choice function has two components. One is the allocation component, and the other one is the payment component. So therefore we are going to also decompose the social choice function into these two components, one of which will be an allocation rule, the function that maps this type profile into an allocation, and the other one is the payment function, which maps the type profile into a real number, which is the payment. So that's quite straightforward. So here is the reason why we have used a capital F, because we are going to use the allocation rule with the lowercase of f, and the payment function is denoted by this p of I, which is a function which maps this type profile. Let's say if the types are theta1 to theta n, then it gives out 1 pi of I, which is the mapped value of this pi acted on this theta1 to theta n, right? So this payment is this is the payment function that we will refer to. Let us now look at some of the allocation rules, just to get a feeling of how these allocation rules look like. The first and maybe the most naive rule is the constant rule, which says that no matter whatever is the type profile, it does not really look at this type. It just outputs one fixed allocation, which is not changing with any of the types. The second one is the dictatorial rule, which we are quite familiar with. So what does this do? It has a predetermined agent or a player whom we call the dictator, and it always tries to maximize the valuation of that particular agent. So whatever is its type, it looks at that type and picks the allocation which maximizes the valuation of that player. It does not look at any other player. But there are some other interesting mechanisms as well. So one of them is the allocatively efficient rule, or also sometimes known as the utilitarian rule. So what does it do? It looks at the sum of the valuations of all the players. So in this case, player I has this valuation function which is denoted by v of I, and if you fix a particular allocation A and the type of player I is theta I, then this is the valuation that player I gets. Now sum it over all the players. So this is the sum of the valuations. Also sometimes this is known as the social welfare. At some point we will also use this terminology, the social welfare of all the players in this setting. And what this allocatively efficient rule or allocation rule is doing is picking that alternative that maximizes the social welfare. So that is one way of interpreting the allocatively efficient rule. Now I should mention that this is different from Pareto efficiency, because Pareto efficiency is a property that is defined over the outcome, and this also considers the payment. But here we are not looking at the payment, we are just looking at the allocation, and therefore these two things are different, even though we will see that we can actually relate these two things. The fourth example that I am going to discuss about is what is known as the affine maximizer rule. It is in some sense a generalization of the allocative efficient rule. The only difference is that now you have a weight for each of these players. So lambda I is the weight, which are non-negative weights, and not all of them are equal to 0. So you are actually taking a sum of all of these things, and you are also doing a translation. So you are adding a factor which is kappa of A, and now this becomes an affine sum which you are trying to maximize. So this affine maximizer rule is trying to maximize this affine sum by choosing the appropriate A in the set capital A. You can see that this affine maximizer rule as a special case gives out the social welfare. This is the case where kappa A is identically equal to 0, and all these lambda i's are equal to 1. That is the social welfare maximizing allocatively efficient rule. You can also get the dictatorship out of here, where for that lambda of d, that distinguished player which is the dictator, it is equal to 1, and for all the other players that lambda I is equal to 0, right? And kappa A is of course equal to 0, identically equal to 0. In that case, what you are left with is essentially this particular expression. So the affine maximizer rule is actually generalizing both the dictatorial and the allocative efficient rules. The last one, last example of allocation rule is what is known as the max-min rule or the egalitarian rule. Okay. So what does it do? It looks at the valuations of all the players at a particular alternative, at a particular allocation. Let's say we are fixing the allocation to be A. It is looking at what is the valuation of all the players under their current type, which is theta of I. Finds out what is the minimum of that. So that is which player is getting the least value out of this allocation, and then picks the allocation which maximizes this minimum value. So in some sense, it is trying to push the bottommost player who has the least valuation out of this allocation, and picks the allocation which maximizes that minimum value. So that is the reason why it is called egalitarian. It is in some sense trying to find a situation where everybody is equally happy or close to equally happy. This is quite a contrast with respect to this utilitarian rule, where there could be some individuals who are having a very large valuation, but there could be some individuals who are getting very low valuation. But because the sum is the maximum, this rule actually picks that, while this max-min rule is actually not picking that kind of an outcome, rather picking the outcome which is not too bad for everyone. On the payment part, we can discuss a few properties. So the first property of payment is that there does not exist any deficit. That is, when you take the sum of the payments of all the players, it must be non-negative. That means if this was less than 0, that means the net payment that was given by the players is actually negative. So that means you are actually paying the individuals for participating in this process, in this mechanism. And the other property is of no subsidy, where so even though there is no deficit, there could be some cases where PIs are negative. So some players are asked to pay a certain amount of money, a positive amount of money. Some players are given payment by the mechanism designer, but no subsidy actually rules out that possibility. It says that everybody should be either paying or not paying any amount of money, but the mechanism designer will never pay any of these individuals. The last property of payment rule is called the budget balance property, which says that the sum instead of being greater than or equal to 0 becomes exactly equal to 0, which means that there is no leftover, there is no additional amount of money that has been generated by the mechanism designer to run this mechanism. It has just been redistributed. So PIs can be both positive or negative. Some people pay money and some people get paid, but overall it is going to be equal to 0. Now let us try to remember the property of incentive compatibility that we discussed quite some time back. So we are going to phrase this incentive compatibility in the context of quasi-linear preferences. So we know that a mechanism in this context is a tuple of the allocation and the payment rule, which is denoted by F and this vector P. So P vector essentially tells you the vector of all the payment functions. Now we are going to call a mechanism f comma p to be dominant strategy incentive compatible if the following thing happens, that is, for all players this inequality holds. And let us try to read this inequality. What does it mean? So as before, we have this theta of I for player I, which in this context we are going to assume to be the correct type of player I. So suppose player I has this type of theta I, then the valuation that this player gets when he reports his type truthfully, and other players are reporting some arbitrary theta minus I tilde, and because this theta I and theta minus I tilde is the reported types, you can also get the payment. Player I also gets the payment for that type profile. Now this left hand side is giving the net payoff to player I when he's reporting his type theta I truthfully, and other players are reporting theta minus I tilde. On the right hand side you have the same expression, except that now that player I has moved to theta I prime, and that is impacting both the allocation and the payment decisions. And this inequality is saying that for all such theta I prime, this left hand side is going to be at least as much as the right hand side. So that means that whenever player I's true type is theta I, there is no reason for player I to misreport his type to be theta I prime, because that is going to give him less net payoff. That is the dominant strategy incentive compatibility. And why is it dominant strategy? Note that this inequality holds for all theta minus I tilde. No matter whether the other players are reporting their types truthfully or not, it's the best response for player I to report their types truthfully. Just to rephrase that, this DSIC means that truth telling is a weakly dominant strategy equilibrium. On certain occasions we will also use this term. We will say that this payment rule P implements the allocation rule F in dominant strategies, or we'll also say that F is implementable in dominant strategies, and it is assumed that there exists some payment rule which is implementing this. So these are just certain terminologies which we might use sometime in the future. One small remark is that in quasi-linear domain we are often more interested in the allocation rule, and that is the reason we sometimes keep the payment rule as implied, because the payment will always exist if the mechanism is implementable. And so we are more interested in this in the allocation rule that we can implement, rather than the whole social choice function, which also includes the payment part. So let us now also look at what is the meaning of the dominant strategy incentive compatibility with a small example. So what are the conditions that needs to be satisfied for a mechanism to be dominant strategy incentive compatible? So let us consider a very small example. We have two players, and both of them have a type set which can take two values, two possible types, either high or low, and the allocation function takes these types and maps them onto the allocation space. Now what should happen if you want to ensure, so what is the meaning if you expand out this expression of incentive compatibility? What do you get in this context? This is just an example to understand what is the meaning of incentive compatibility, the set of inequalities that we need to satisfy for that. So the first expression, so let us just look at the first expression. The rest of the expressions will be quite obvious the way we have written it. So the first expression says that the value of player 1, when the player has the type of theta of h, and when he also reports this type in a truthful manner, that is theta of h is what he is reporting, and player 2 is reporting something, any theta 2, then the value, the net payoff that player 1 gets is at least as much as the same expression when the same player has the true type to be equal to theta of h, but he is actually misreporting to theta of l. So note that only the allocation rule and the payment rule are dependent on what is being reported, because the mechanism designer has only access to what has been reported. It does not know what is the true type. And this expression is from the point of view of the player, because the player knows what is the true type, and it is trying to compare what will happen if I misreport versus if I do not misreport. And this inequality is saying that it is better not to misreport, because the net payoff is not going to be larger if he misreports. And this inequality holds for both these theta 2's. So essentially this inequality has two inequalities in it. One is for theta 2 being equal to theta of h. The other one is theta 2 being equal to theta of L. Now you can apply the same thing when player 1 actually has a true type, which is theta of L, which is theta of low. In that case, the truthful report is theta of L, and that will be on the left hand side. So in that case, this expression, this utility is actually going to be larger than if he has his true type is theta of L and he is reporting theta of H. Similarly, you can write the expression for player 2 in a very similar way. So that is the interpretation of the DSIC mechanism for two players and two types. So let us now discuss a couple of properties of the payment that implements an allocation rule. So let us say that this mechanism f comma p is incentive compatible. Then let us try to think about what will happen if we consider another payment function which has the same payment as before, the same pi of theta I theta minus I, but it also has an additive constant which is hi of theta minus I, and h. So notice this carefully, that it does not depend on theta of I, not dependent on theta of I. So that is an important thing. Now the question is, can we actually say, what can we say about this mechanism? So is that mechanism dominant strategy incentive compatible? The answer is yes. And why is that? That is precisely because of the reason that hi does not depend on theta of I. So it does not really matter whether player I has reported it truthfully or untruthfully. It is always going to be cancelled out from both these sides, right? And the inequality that we are already getting satisfied for f and p, because we have already assumed that this is going to be incentive compatible, then this inequality will always hold. If you just add another hi of theta minus I tilde, it does not really matter. It does not really change any of the properties. So the conclusion is that if we can find a payment which implements an allocation rule, then we'll immediately get a very large set of payments, actually uncountably many payments, which can also implement that allocation rule. The harder question is actually the converse question. So when can we actually have the payments that implements f differ only by a factor of hi of theta minus I? And this is a question that we'll address sometime later. So at this point, I'm just keeping you interested in the converse question. The other implication of incentive compatibility on payment is the following. Suppose we have an allocation that is same in two different type profiles. So one type profile is theta, where you have theta I, theta minus I. The other profile is theta I tilde, where you have theta I tilde. So only player I's type has changed. For the other players, the types are still the same. So that's the only difference. Player I is the only change in these two different profiles. And the outcome, the allocation, is the same, let's say A, in both these two cases. Then if we assume that P implements F, this payment function implements this allocation rule, then the claim is that the payment must also be the same. And I leave it as an exercise. All that you really need to do is to appropriately write down all the conditions, conditions for incentive compatibility to prove this result.